So now let's go to the non-pre-stressing reinforcement. So non-pre-stressing reinforcement consists of bars. This is the bar, wires, and welded wire fabric, all of which are manufactured in accordance with ASTM standards. So these are the common non-pre-stressing reinforcement we usually use in pre-stress concrete design, and actually on any other design like reinforced concrete design, but more usually commonly used on pre-stress concrete design. And again, these materials here, you can see here, non-pre-stressing reinforcement, are all manufactured in accordance to ASTM. So ASTM stands for American Society for uh, Testing and Materials. To increase the bond between concrete and steel, projections called deformations are rolled up onto the bar surface in accordance with ASTM A616-96A for the bars to be accepted as deformed. So the bars that we usually use as non-pre-stressing reinforcement for pre-stressed concrete members or concrete element are usually have a what we call deformations like this one. Actually, we have different kinds of deformations that we usually put on the bars that we use as non-pre-stressing reinforcement for the purpose of increasing the bond between this steel, these non-pre-stressing reinforcements, and the concrete that will eventually cover them when you pour the concrete upon them. So that is the purpose of deformations for bars. So those deformations must be in accordance with ASTM A616, the standard specification for rail steel deformed and plain bars for concrete reinforcement. Deformed wire has indentations pressed into the wire or bar to serve as deformations. So if for the case of bars, the deformations will look something like this, any of this, depending on the manufacturer. For the case of the wires, the type of the deformation that being put on wires are actually indentations that look something like this, to again with the purpose of to increase the bond between the non-pre-stressing reinforcement or the wires and the concrete that will eventually cover them when the concrete is poured on them. So these are the different properties of the reinforcing steel, the non-pre-stressing reinforcement. So the first on the list is Young's modulus, the modulus of elasticity of steel, the yield strength or the Fy, F sub y of steel, the ultimate strength of the steel, the Fu, the steel grade designation, and the size or diameter of the bar or wire. So this figure shows typical stress strain curves for grades 40, 60, and 75 steels, which have yield strengths of 40,000, 60,000, and 75,000 psi respectively. So this is actually the stress strain curve. This is what a stress strain curve for steel looks like. So this is for bars, this is for wires. For these are actually for grades 40, 60, and 75. Grade 40, 60, and 75. Actually, the naming, the grading of the non-pre-stressing reinforcement actually has something to do with their corresponding yield strengths. Like for example, for grade 40, when we say grade 40, its yield strength is obviously 40 KSI, kips per square inch, or 40,000 pounds per square inch, because 1 kip is equal to 1,000 pounds. For grade 60, the 60 there means the yield strength of grade 60 is equal to 60,000 psi. And for grade 75, it means 75 psi is the yield strength of that particular grade of non-pre-stressing reinforcement. So you can see here that although similar to the stress strain curve of concrete, almost similar except for this particular part. So as you increase the stress or the force being applied to the steel, tendency is the stress will increase obviously, and then it will reach a limiting point here, and then after that limiting point, the proportional limit, it will eventually reach another limit, which is the elastic limit, wherein it ceases to be elastic if the stress will be greater than that elastic limit. And then after that elastic limit, uh, there's a point there that what we call yield point, wherein the stress strain curve starts to be like horizontal in nature, meaning there is no corresponding increase in stress, but there's still a increase in strain for that particular portion of the stress strain curve. And then after some time, it will eventually regain its strength until such time that it will reach this maximum point on the stress strain curve, which is actually what we call the ultimate strength of the steel. And then after that, it will eventually fail, or will experience rupture. For steels that lack a well-defined yield point, the yield strength value is taken as the strength corresponding to a unit strain of 0.005 for grades 40 and 60 and 0.0035 for grade 80 steel. Because as I mentioned a while ago, the proportional limit, elastic limit, and the yield point actually are almost very near from each other in terms of this stress strain curve. So actually, the yield point or the yield strength is very hard to be defined or determined. So in those cases wherein there is no well-defined yield point, we usually specify the stress corresponding to the strain of 0.005 as the yield strength of that particular steel for grades 40 and 60. For grade 80, we will just have to find the stress corresponding to a strain of 0.0035. So like for example, you will just have to find the corresponding strain here and then point to the stress strain curve and then check for the corresponding stress on that particular point for that particular strain. The ultimate tensile strengths corresponding to the 40, 60, and 80 grade steels are 70,000, 90,000, and 100,000 psi respectively. So those are the ultimate strengths of these grades of steel reinforcement or non-pre-stressing reinforcement. Actually, you can refer to this table if you want to find the corresponding ultimate strength and the yield strength of certain type of non-pre-stressing reinforcement. For most mild steels, the behavior is assumed to be elastoplastic and Young's modulus is taken as 29,000 KSI or 200 GPa. So usually we assume that the modulus of elasticity of non-pre-stressing reinforcement is equal to 200 GPa, gigapascal, or 29,000 KSI. So now we're done with that goal. We are already familiar with the different properties of non-pre-stressing reinforcement. Now, let's move on to our last goal for this meeting, which is to be familiar with the different properties of pre-stressing reinforcement.